Welcome to Pre-AP Chemistry with Miss Williams. Today we will be looking at Lesson 1.7, Investigating Heating Curves, Heat of Vaporization. First, we will be looking at a heat of vaporization demo. Next, we will use our experimental data to walk through a heat of vaporization calculation. When we're all done, you will be completing a heat of vaporization check for understanding Google form. Let's get started. First, let's review our learning intention and success criteria. Learning intention and success criteria. Students will learn how to apply the first law of thermodynamics to their analysis of heat transfer during phase changes with the use of quantitative methods. Students will be successful if they are able to analyze a heating curve of an unknown substance using quantitative data as well as their understanding of the first law of thermodynamics. Last class, we looked at the heat of fusion of ice. The heat of fusion of ice is the joules of energy needed per gram of ice for it to melt. The heat of vaporization of water, on the other hand, is the joules of energy needed per gram of water for it to vaporize. Let's take a look at a heating curve of water. Remember, this is made based on standard atmospheric pressure, and boiling and melting points will be different at a different pressure as we saw in phase diagrams. Let's zoom into the vaporization section of the heating curve to take a closer look. Notice how the temperature continues to increase as the liquid heats, but stays constant as it vaporizes. Remember, the heat is the energy that is put in, and the temperature is the measurement of the movement of the particles. This tells us that as the water is gaining heat through the liquid phase, the movement, known as kinetic energy, increases. It also means that as the water enters the vaporization stage, the potential energy increases while the kinetic energy remains the same. This input of energy into a phase change disrupts the attraction between particles, allowing the more free particle movement found in a gas. This also gives us a challenge, though. How can we calculate the energy needed for this phase change if the temperature itself doesn't change? This could be a little tricky to measure on its own, but thanks to the first law of thermodynamics, with a little math, we can determine the heat of vaporization of water. Imagine for a moment two identical beakers on a hot plate. The only difference between them is the amount of water in them. If we assume that the hot plate evenly distributes energy as heat to each beaker equally, what would be true for the amount of energy each beaker receives? I'll give you a few moments to think about it. If the two beakers are identical and receive equal heating, we can assume that each beaker receives an equal amount of energy. That means that we can use the amount of temperature change that occurs in the more full beaker over the time it takes for the smaller beaker to go from boiling to vaporize to determine the energy it took for vaporization. That can be a lot to think about. Let's watch a lab demo to see the process in action. Welcome to the heat of vaporization demo. In this lab, we will be determining the heat of vaporization of water. We will do this by heating two identical beakers with different amounts of water on the hot plate. We will measure the change in temperature of the more full beaker during the time it takes for the less full beaker to vaporize. This will allow us to calculate the amount of energy needed for the water to vaporize. Let's take a look. To start, we are going to be putting 100 milliliters of room temperature water in one beaker and 5 milliliters of room temperature water in an identical beaker. Next, we are going to quickly place both beakers on the hot plate and watch carefully for the first sign of the 5 milliliter sample to begin boiling. Once it starts to boil, we will record the temperature of the 100 milliliter sample as our starting temperature. Here, our 100 milliliter sample is at 25 degrees Celsius when the 5 milliliter sample begins to boil. And now we wait. Here's some music for you to enjoy while you watch water boil. Once the 5 milliliter sample has almost completely vaporized, make sure to pay attention to the temperature of the 100 milliliter sample. Once the 5 milliliter sample is completely vaporized, record the temperature of the 100 milliliter sample. This is your ending temperature. Here, our ending temperature is 51 degrees Celsius. We now have everything we need to complete our analysis. First, we will need to use the specific heat, Q equals MCAT equation, to determine the joules of energy transferred to the 5 milliliter sample during vaporization. We can do that by calculating the Q for the 100 milliliter sample. To do that, simply multiply the mass of 100 grams by the specific heat of water and then by the difference in ending and initial temperature. Once we have determined how much energy was transferred to the 100 milliliter sample, we can use that for the joules in our heat of vaporization equation, since both beakers receive the same amount of energy. That's it. Let's go through the math together and see how we did. When the 5 milliliter sample began to boil, our 100 milliliter sample was at 25 degrees Celsius. When the 5 milliliter sample had vaporized, our 100 milliliter sample was at 51 degrees Celsius. First, we need to use the specific heat Q equals MCAT equation to determine the joules of energy transferred to the 5 milliliter sample during vaporization. We can do that by calculating the Q for the 100 milliliter sample. To do that, simply multiply the mass of 100 grams by the specific heat of water, and then by the difference in ending and initial temperature. Let's start with what we know. The mass of our 100 milliliter sample was 100 grams. The specific heat, or C, of water is 4.18 joules per gram degrees Celsius, and our 100 milliliter sample had a final temperature of 51 degrees and initial temperature of 25 degrees. I'll give you a moment to calculate the change in temperature for the 100 milliliter sample. If you got 26 degrees Celsius, you are correct. Now, let's replace our variables with our knowns. Our mass is 100 grams. Our C, or specific heat of water, is 4.18 joules per gram degrees Celsius. And our delta T, the change in temperature of the 100 milliliter sample, was 26 degrees Celsius. The next step is to multiply them all together. I'll give you a moment to make the calculation yourself. If you got 10,868 joules, you're right. Now we're ready to calculate the heat of vaporization of water using our 5 milliliter sample. For the joules of energy, we will use the Q we just calculated for our 100 milliliter sample since we're assuming they received equal heat energy. The G is grams and refers to the mass of the 5 milliliter sample that vaporized. Since 1 milliliter of water is equal to 1 gram of water, our 5 milliliter sample that vaporized had a mass of 5 grams at the start. To calculate the heat or vaporization, simply divide the joules of energy by the mass of the 5 milliliter sample. I'll give you a moment to make your calculation. If you got 2,173 joules per gram, you're correct. This means that for every gram of water, 2,173 joules of energy is needed for the water to vaporize. Let's see how this compares to the accepted value of the heat of vaporization of water. The heat of vaporization of water has an accepted value of 2,260 joules per gram. I wonder how much we were off. To do this, we will use the percent error formula. Percent error is the difference between the actual value you observed and the expected value based on reference. If you look up the percent error formula, you'll probably find something like this. This equation means that the percent error is equal to the absolute value of the actual value you observed minus the expected accepted value divided by the expected accepted value, all multiplied by 100. Let's work with it using more common language. The A and E you see next to HVAP is to keep our values organized. Let's start putting in our known values. First, we'll put in the actual value we got during our lab, 2,173 joules per gram. Next, we will put in what it should be, the expected accepted value of 2,260 joules per gram. The difference between what we got and what it should be is negative 87 joules per gram. You could use the absolute value of 87 joules per gram too. Next, we will compare that difference to what it should be, the expected accepted value of 2,260 joules per gram, by dividing them. That gives us a value of negative 0.038. All that's left is to multiply by 100. That gives us a percent error of negative 3.8%, which means our value was pretty close. A percent error of less than 5% is generally considered an acceptable percent error. Now it's your turn to share what you have learned today by completing the heat of vaporization check for understanding assigned to you in Google Classroom. In the heat of vaporization check for understanding form, you will use the provided table and heating curve to respond to a series of conceptual questions. Your to-do list is 1. Open heat of vaporization check for understanding Google form in Google Classroom. 2. Examine the table and heating curve. 3. Using what you have learned, respond to the questions on the form. 4. Submit the Google form when you're done. Today's learning intention and success criteria. Students will learn how to apply the first law of thermodynamics to their analysis of heat transfer during phase changes with the use of quantitative methods. Students will be successful if they're able to analyze a heating curve of an unknown substance using quantitative data as well as their understanding of the first law of thermodynamics. Remember your to-do list. 1. Open heat of vaporization check for understanding Google form in Google Classroom. 2. Examine the table and heating curve. 3. Using what you've learned, respond to the questions on the form. 4. Submit the Google form when you're done. And as always, don't forget, have a great day, MHSA.